Hey everyone, welcome back. We are to the basics of antiderivatives. Um, I started out with this breakdown of derivative rules. So this is from last chapter, chapter 2, where we have all of our derivative rules. The constant multiple means the constant can actually come out before I take the derivative and then take the derivative. That's going to matter with the integrals here in a minute. If I'm adding or subtracting between, then I can break them up into two separate derivative rules. Power rule, I mentioned in a previous video. We're going to do that. The derivative of a constant is 0, and derivative of x is just 1. Derivative of e to the x is e to the x, and derivative of ln of x is 1 over x. So now we're going to go backwards from that, and this is where the main piece comes in. So if I have a constant times my function, I can pull that constant out in front before I do the antiderivative. I do this all the time. I like getting many of the constants out from the integral. It makes it less confusing to me. I also use a rule B here, where I actually break it up into two separate integrals. This should be a G. I don't know why that's another F. And that way, and any constants I pull out of those as well. So I can really focus in on the antiderivative rule. The big one, this is the huge one that we're going to be using mostly today for this video, is here. And I noticed a big typo. This should be n is not equal to -1. Please correct that in your notes. And if the integral of a constant, but then we just get that constant times x. And then we have our plus c, of course. We talked about that in the previous video, where it's called a constant of integration. Integral of e to the x dx is just e to the x plus c. And the integral, just to be clear, this is the integral of 1 over x dx, which we see here, becomes the natural log. And be careful, this is the absolute value of x. And that will matter eventually. I'm going to give some examples using the power rule that I highlighted. If I have the integral of x squared dx, this is going to be 1 over 2 plus 1 x to the 2 plus 1 power, which is 1/3 x to the 3rd plus c. That's not too bad. And again, if that wasn't a 2, if it was a 5, then it would be 1 over 5 plus 1, x to the 5 plus 1, and so on. Where it gets a little tricky is if we have the integral of x to the 1/2 power, then that's going to be 1 over 1/2 plus 1, x to the 1/2 plus 1 plus c. And because we have fractions, it gets a little bit muddied there. So just be careful. And in fact, let's go even further. Do the integral of x to the -1/2. Let's make it -1/3. Something different. -1/3 plus 1 gives me 2/3. This gives me 3/2 x to the 2/3 plus c. So you can see the power rule is very useful, very easy, but it can get very clunky. And so we'll need to be sort of extra careful as we're looking at that. I want to move on to some specific examples. And this page is way too crowded. So what I'm going to do is I'm going to switch to another page and work them each out individually. So what I'm going to do for this first one is pull up a blank page. And so for our number 1, I want to integrate from 3 to 5, 6x plus 7 dx. Now I want to go kind of slow on this. I'm going to break this up into two separate integrals, and I'm going to pull the constants out. And so this is using some of those rules where I can break this down. And you might be asking yourself, why would you do that? Well, I just want to focus on the x dx and the dx. I'm going to notice that x to the 1 power becomes 1 over 1 plus 1, or x squared. And I'm going to evaluate this from 3 to 5, plus 7x. So the integral of dx is just x. Now, there's not a plus c on this one. This is called a definite integral, meaning we have boundaries. So we don't end up with the plus c. We only end up with the plus c if we have no boundaries. So problems 2, 3, 4, not 5, 6, 7, not 8, not 9, but 10, and not 11 or 12. So those are all indefinite integrals. So we'll get to all of those. So let's simplify this a bit. This is going to be 3x squared from 3 to 5 plus 7x from 3 to 5. This is going to become 3, 5 squared minus 3 squared. This is, again, that fundamental theorem of calculus from the previous lesson, plus 7, 5 minus 3. I'm getting 62 as a final answer. Please double check my numbers. So here's our first indefinite integral. Definite integral, pardon me, because we have boundaries. A definite integral. We'll move on to problem 2. Here's our indefinite, meaning we're going to need that plus c now. And I'm going to go ahead and pull that constant out again. And we know that the integral of e to the x is just e to the x, right? Because its derivative of e to the x is also e to the x. So we end up with the same thing back. But I got to remember my arbitrary constant there, that plus c. That is important. Part 3, we have the integral of 6 over x dx. And once again, I'm going to pull that constant out in front. If we look back on the previous sheet, we can see that the integral of 1 over x dx is just 6, and then we have ln of the absolute value of x plus c. Number 4, I have the integral of 4x cubed plus 2x to the 4th dx. And I'm going to use my rules where I'm going to break it up into individual integrals, and I'm going to pull the constants out. You don't have to do this, and many teachers teach this in a way that they don't break it down like this. This is just a personal preference. And x cubed, the integral of x cubed, is going to be 1/4 times x to the 4th plus 2 times. Integral of x to the 4th is going to be 1/5 x to the 5th. And now I need my plus c. We end up with our final integral is here. Don't forget that plus c. That's after you integrate. Number 5, we have the integral. Now we have a definite integral where we have boundaries. And I'm going to rewrite this a little bit differently to make it a little bit more clear. This becomes x to the negative 2nd power dx. I'm now going to use the power rule, and I'm going to break it down. That's going to go from 2 to 8. Again, notice there's no plus c because we have a definite integral. And simplifying it up, I get to here. And I'm now going to go, this becomes negative 1 over 8. Now be careful, minus negative 1 over 2. So we get that minus minus situation going on here. Be careful to get a common denominator when you're adding or subtracting fractions, of course. And I'm getting 3/8 as an answer. And notice when we have a definite integral, we end up with a number as an answer. And when we have an indefinite integral, we have a function, in this case, a function of x each time. So number 1, we have a number. 2, 3, and 4, we have functions. Number 5, we have a number because it's a definite integral. Number 6. All right, we have kind of a long one here. We have all that. And I'm going to break this up into several simple separate integrals. And I'm going to pull their constants out in front as well. So the divided by x to the sixth I brought up to be x to the negative sixth, and the root x I made the 1/2, and I pulled the 3, the 2, the 6, and the negative 3 out in front of the integral. So now I have 4 smaller, easier, hopefully, integrals. And this one I'm going to break down a bit more. This is going to be 1 over negative 6 plus 1, x negative 6 plus 1. Minus 3, I'm going to break this one down as well. And all that ends up with a plus c. Now you might be asking yourself, don't each of those have their own plus c? They do, but I'm going to take all those constant and mash them all down to the end, so we just have one giant constant towards the end. So let's try to simplify this up a little bit. And this becomes minus, this becomes 6 over 5, x to the negative 5th power. And this becomes minus 3 times 1/2 plus 1 is 3/2. This becomes 2/3, x to the 3/2. And I'm going to clean that up just a little bit more. And if you want to bring that x to the negative 5th down to the denominator, that's okay too. I'm going to reduce these 3's now. We're just going to get 2x to the 3/2 plus c, and that is going to be overall our big, huge answer. All right, let's move on to number 7. We have the integral of 6 over x squared plus 3x plus 4 dx. And once again, I'm going to break this down into several smaller integrals. And with this one, again, I'm going to take my time. Now, the integral of x becomes 1/2 x squared, so this becomes 3/2 x squared plus 4x plus my constant. And let's clean that up a little bit. So that becomes 1/-2 plus 1 is -1. So this becomes -6 x to the -1 power. And we could clean that up a little bit and rewrite that as -6/x. But the way we have it here is just fine. Of course, listen to your teacher. If your teacher insists that you bring that down, then make sure you bring it down. Some teachers care, some teachers don't. I obviously am one that do not. All right, so we have a definite integral now for number 8. All right, and I'm going to break this down a little bit. I'm going to bring that 3 out. And I'm going to note that the integral of 1/x dx becomes the natural log of x This is going to become 3 ln of e to the 5th minus ln of 1. Now, you might notice that I dropped the absolute value. E to the 5th is a positive number, so I don't need the absolute value. And 1 is also a positive number, so I don't need the absolute value. You can keep it. It's not wrong to write, but it's not necessary. Now, the natural log of 1 is 0. So this part right here becomes 0. Also, you might remember that if you have the natural log of e of something, that just becomes 3 times whatever that exponent is in this case. So the answer in this case is 15. Number 9, we have another definite integral. So we're here. Once again, I'm going to break this down into 2 separate integrals with the constants out in front. And I'm going to integrate x cubed is going to give me 4 times 1/4. And that's 2 times 1/4, x to the 4th from -3 to 2, plus 7/8, x to the 8th power from -3 to 2. Now we're going to have to be really careful as we're looking at this with all these negatives. And I want to caution you, you might look at that and go, you know what, that's minus minus, so that becomes plus. Nope. Remember, exponents come first. And because -3 to the 4th power is going to become a positive 81, that's still going to be 2 to the 4th, which is 16, minus 81. Be really careful. So this is not the minus minus situation because you have to deal with the exponent first. 2 to the 8th, I believe is 256. Let's double check that. 2 raised to the 8th. 256 minus, now that becomes a positive 8 to the 3rd, or 3 to the 8th. That's 6561. And let's keep going. We got to be really careful with these constants here. So 16 minus 81. So I'm getting negative, what was it, 65/2 plus, let's see, 256 minus 6561 times 7 divided by 8. So this is going to become minus 44135 over 8. And I'm going to go 65 times 2. Oops, 65 times 4, pardon me, to get a common denominator. I'm going to add that to the 44135. This becomes, let's see if I can squeeze it in here. So we get this big, ugly number. And it's negative. Be really careful with the minutia here. I'm looking at my wife's notes as I'm doing this, and she went a different route. We ended up with the same value, of course, but meaning that there's more than one way to evaluate this and still come to the same conclusion. All right, let's move on to number 10. We have the integral of x plus 4, x minus 2 dx. And I'm going to FOIL that first. Don't break that up into x plus 4 dx times x minus 2. It doesn't work that way. The multiply does not work that way. If you look at the rules, there's no multiply rule. So this becomes x squared plus 2x minus 8, it looks like, dx. And that, all I'm doing is just foiling that together. And now I'm going to integrate each one of those. Integral of x squared is going to be 1/3 x to the third. Integral of x is 1/2 x squared. So this gives me plus 2 times 1/2 x squared minus 8x plus c. And we are to number 11, which is going to be a little tricky. And this is the last one before our word problems. We have another definite integral. And I want to off to the side here, just remind us that x squared divided by root x And why do we need that? Well, what I'm going to do is I'm going to break this up actually. Into this. Notice I pulled the 6 and the 4 out in front. And I'm going to clean that up a little first. X squared over root x, I just did in the blue to the side there. And I'm going to really break this down using the power rule for each of these. So Here, 5 halves plus 1 is 7 halves, so that's going to be 2 over 7. It's going to be 4. Negative 1 half plus 1 is 1 half. 1 over 1 half is just 2. That's going to be x to the 1 half from 1 to 8. Remember, 1 to any power, or the any root of 1 is always just 1. Just keeping that in mind. Remember, x to the 1 half is just square root. And both of these, to be clear, just become 1. Not 0, they become 1. Oops, that should be plus. That is very, very, very messy. But I'm just going to leave that there. We can clean that up a little bit more. Remember, root 8 is, we can pull some 2's out and stuff, but this is fine. All right, and we are to our word problem. Yay. Number 12. It says the traffic flow rate, cars per hour, across an intersection is R of t equals 200 plus 700 t minus 150 t squared, where t is in hours, and at 6 a.m. t is 0. How many cars pass through the intersection between 6 and 7 a.m.? Okay, that means my boundaries are going to go from 0, because at 6 o'clock, that's t equals 0. So at 7 o'clock, that's t equals 1, meaning 1 hour has passed. And so this means that we're looking at the integral from 0 to 1 of 200 plus 700 t minus 150 t squared dt. Now, you might think to yourself, oh, this one's t, all the others were x's. It doesn't matter. As long as the variable matches up, all the same rules are going to apply. All right, I'm going to break this down. And so the integral of dt is just t, so 200 t, and t is going to go from 0 to 1. Plus now 700, and then integral of t is going to be 1 half t squared. So this is going to be 700 halves t squared from 0 to 1. Now, integral of t squared is going to give me 1/3. 1/3 of 150 is 50. T to the third from 0 to 1. Again, this part here becomes 1/3 t to the third. And 1/3 times the 150 is just the 50. In case you thought I skipped too many steps. Oops, undo. So the 1/3 times negative 150 gives me the negative 50. And evaluating this from 0 to 1, this is going to be 200, 1 minus 0, plus 700 over 2, 1 squared minus 0 squared, minus 50, 1 cubed minus 0 cubed. And of course, 1 to any power is 1, 0 to any power is 0. So this just ends up being 200 plus 700 over 2 minus 5. And you know what? 700 over 2 is actually just 350 when you divide it out. And so when we add that up, that's going to be That's going to be 300 plus 2. That's going to be 500 cars. I like how all these numbers kind of very, very pretty work themselves out. In real life, of course, that doesn't quite work out that way. In our last problem, number 13, a company's marginal cost. So our marginal cost is 20 over root x, and I'm going to rewrite that as 20x to the negative 1/2 power, where x is the number of units. Find the total cost of the first 25 units. So the cost, in this case, is going to be the integral from 0 to 25, and I'm going to pull the 20 out of x to the negative 1/2 power dx. This becomes 20 times 1 over negative 1/2 plus 1. Excuse me again. And this becomes 20 times, this becomes negative 1/2 plus 1 is 1/2. The reciprocal is just 2. And this becomes x to the 1/2 or square root of 0 to 25. This becomes 4 times root 25 minus root 0. So it looks like we are just getting, oops, that should be 20 times 2 is 40. And then 40 times root 25 is just 5, which is $200. Is the total cost of 25 being made. Super cool. A few applications there. We'll get a few more in some other sections. See you then.